Hello everyone, my name is Iterative. I'm a PhD candidate at University of Wisconsin-Madison, and this work is a collaboration with Aju University. Today, I'm talking about a new problem that prevents adoption of emerging quality scalable or iterative hardware architectures, despite their advantages in energy saving. This is because there is no existing efficient method to determine the iterative hardware latency. Then I present our proposed scheduling solution, which achieves optimal or near optimal latency for the iterative hardware. With traditional computation methods, our design space has two dimensions: energy efficiency and performance. Preferably, we are looking for designs that are energy efficient with high performance. However, with approximate computing, that the correctness of the result is not guaranteed, another dimension makes our design space a 3D one. This additional dimension allows for having simpler, faster hardware and software solutions, and brings more opportunity to save energy or to enhance the performance, as well as improve application-level quality when limited resources are available. And there are plenty of new popular error-resilient applications that are happy with the good enough solution, such as signal processing, data mining, machine learning, or HCI applications. Early approaches to approximation were mostly design time. For example, a circuit-level approximation technique called MPACT saves energy by reducing the number of transistors, trading the accuracy of the result. Unfortunately, design time techniques support only a single level of accuracy and do not support dynamic quality configuration. In other words, once the design is fixed, there is no control knob for adjusting the accuracy at runtime. On the other hand, accuracy requirement is variant, and to maximize the energy saving, we demand runtime quality scalable hardware techniques. Iterative computing is an approximation approach that progressively improves the output quality over multiple iterations. Using iterative computing hardware, one can either achieve high accuracy by allowing for more latency or high power efficiency by finishing computation sooner. This example shows an approximate iterative divider called SADI. If the accurate division result is 30.6, SADI could achieve 29.8 at first cycle, 29.9 at second cycle, and 30.5 at fifth cycle. To take advantage of this approach, various iterative computing hardware designs have been proposed. However, in spite of the benefit, the adoption of iterative computing hardware has been prevented by the lack of an efficient method to determine the optimal latency of them to meet the energy and quality requirement at the same time. There are two major challenges to determine the optimal latency for iterative hardware. First, the accuracy of approximate computing hardware varies significantly depending on their input. Changing from one dataset to the other changes the output error quality. Moreover, most applications consist of multiple interdependent computations. These make the accuracy estimation a challenging task. Second, there are a sheer number of all possible solutions. And that is why naive design space exploration methods such as exhaustive search is impractical. And in fact, an optimization technique is required. Unfortunately, there exists no prior optimization method solving the problem of scheduling of iterative computing hardware. In this paper, we propose an integer linear programming or ILP-based scheduling method to address these two challenges. We consider the input dependence of output accuracy by using a data-driven error modeling to estimate the error. We demonstrate that the proposed method successfully finds the optimal or near optimal latencies for iterative hardware, orders of magnitude faster than exhaustive search or decision tree. In a FIR32 filter application, it only takes 19.4 seconds to perform the optimization, whereas it could take around 10 hours with decision tree method. Before I move on to the detail of the paper, let's see an example of a scheduling problem together. Here we have a 5-tab FIR filter application with a small data dependency graph. Dark gray nodes are approximate iterative multipliers, where they can be configured to 1 or 2 cycles. Light gray nodes are precise adders with only one cycle to choose from. The scheduling problem is to find the start time of each operation and their latency. Depending on the latency constraint, we could have more cycles to assign to multipliers. The solution to this example problem could be the number of cycles for multiplier M1 to M6. As you can see in this table, if we have 7 cycles, which is our minimum latency, all operations assigned to run for 1 cycle. If we have 1 more cycle to spare, the problem would be choosing among those 6 multipliers to assign the extra cycle. As the number of solutions increases, the problem would be harder to solve. We continue on the last example to describe our data-driven error model. Assume that we have 1 extra cycle and we want to choose a multiplier to assign that extra cycle to. Which one would be better? Our main objective is to have less error at the final output or Q. For that, we need to calculate the error at Q, but how? We can run the application and find the exact error, which is extremely time-consuming and impossible for an optimization technique, or we can estimate it. Here, I have our error propagation model. We want to estimate the error at the output of node C called Q. Node C has 2 inputs, A and B. Node A and B each have errors, epsilon A and epsilon B. Node C itself is an approximate operation. In this case, it is an approximate multiplier with error value of delta C. The error at Q computes as the square root of sum of squared errors epsilon A, epsilon B, and delta C. This model is based on uncertainty propagation error model in multipliers and is easily transferable to other operations such as division. The operation error rate delta C is input dependent. Our data-driven error model annotates the data dependency graph of application with delta values. In this example, delta M1 to delta M6. Now let's see an overview of a scheduling problem. Our target hardware can consist of precise hardware with fixed latency and iterative computing-based approximate hardware where the latency is to be determined. We model the data dependency of application in a directed acyclic graph or DAG format. Then the scheduling problem is given a total latency constraint to find the optimal starting time and the latency of each operation that minimizes the error rate of the final output. To solve this problem, we propose an ILP-based scheduling optimization. Given that overview, now I present the details of ILP formulation. The inputs to the optimization is first the error annotated application DAG by our error model, and the second, latencies of approximate hardware units at different approximation level. We constrain the optimization by providing the first number of available hardware unit per operation type, second, the data dependencies in application in form of DAG, third, latency of each node in application, and last, the application total latency. Our objective is to solve the problem to find a starting time and latency of each operation in application that minimizes the error rate of final node. Finally, it is time to evaluate the proposed method. We use 2 types of benchmark application: finite impulse response or FIR filter and polynomial evaluation or POE. We consider the normal input data distribution for error model, but it could be any other distribution as well. We use a recently proposed approximation iterative multiplier called TIM in our hardware model. We evaluate the scheduling efficiency in terms of mean relative error or MRE of application output. The execution time is measured on a PC with 3.4 GHz quad-core Intel Core i5 CPU with 16 GB of RAM. Groovy is used as ILP solver. Here we see the DAG of N-tab filter and nth order of POE. In the table, I have the number of adders and multiplier in each application. For example, FIR32 has 33 adders and 32 multipliers. Considering that each multiplier could use up to 2 cycles, therefore minimum latency for FIR32 application is 34 and the maximum could be 65. Last row includes the total number of scheduling solutions for these applications. Even a small application like FIR16 has around 130,000 solutions to explore. This number grows exponentially with more number of operations in application. We evaluate the optimality of a scheduling solution in these figures. On the top is for the top one is for FIR5 and the bottom one is for POE6. The x-axis has the scheduling solution index sorted in ascending order of their corresponding MRE values from left to right. It means the optimal solution is index 1. And the y-axis counts the application total latency constraint. If you recall the example for a scheduling problem that I presented for FIR5, for latency of 19, we have 15 different solutions to choose from. The ILP could successfully find the optimal solution in most cases, such as latency 9 in FIR5. And in cases it's not optimal, the MRE value of found solution is near the MRE value of optimal solutions, such as latency 10 in FIR5. We evaluate the optimality of scheduling for more benchmarks compared to exhaustive search or decision tree where exhaustive search is not possible. The proposed scheduler solution also achieves good accuracy for larger benchmark as well at a much lower execution time shown in next slide. We evaluate the execution time of proposed scheduling against the measured or estimated execution time of others. The proposed scheduling method dramatically reduces the execution time by more than 1 billion times for the complex benchmark. Our proposed error modeling relies on the distribution of input known at design time, but the actual input at runtime may be different and may have a different optimal schedule. To investigate the impact, we evaluate the optimality of a scheduling solution that are optimal for one dataset when applied to another. All benchmark result in the same or only slightly different optimal solution, as shown in this table, in spite of having different input distribution and error model. With that, I conclude my talk and thank you for listening to my presentation.